Ionization energy is the energy required to remove an electron from an atom to make it into an ion. And really, we're talking about a positive ion. What's the energy required to take that electron away from that atom? That is the ionization energy. Some atoms, very easy. Some elements, easy to take electrons from. Other elements, near impossible to take electrons from. Ionization energy will increase from top to bottom. It's harder to remove an electron as you move up a column. It takes more energy to take an electron as you move up a column, basically. And that goes with the shielding. There's a lot more shielding here than here. So those electrons are much closer here with neon to the positive nucleus than they are with cesium. Cesium is much farther away. So it's going to take a lot more energy because those are closer to the nucleus as we go up the ladder. As we go from left to right, increasing ionization energy, that means it's harder to take an electron from these guys. It takes more energy to take an electron here. We go from right or left to right. It takes a lot more energy to grab an electron. It's really easy to get an electron from these guys, especially down here. Much harder up here to get an electron. Now, why, when we go from left to right, is it more difficult? Or do we need more energy to get an electron? Well, it all has to do with these guys, the noble gases. The noble gases are filled. Their energy electrons are filled. They have no more room. They are cool. They are stable. There's no way in heck, because they're the cool kids now, are they going to give up an electron? Because they have a filled outside valence shell that they are cool. It's because they have that filled valence shell that they are stable. They don't react. These guys have their energy levels filled, their outside energy levels filled. There's no way in heck you're going to get one from them. It's just like the cool kids. Finally, if you're a cool kid, there's like no way dethroning them. Now go over here. These guys they're in group 7, remember, so they have 7 valence electrons. They only need one more electron, and they'll be cool. Look at fluorine. Fluorine just needs one more, and it'll have its outside valence shell just like neon. If fluorine could get one more, it'll be cool. It'll be noble. It'll be stable. So it's going to be really hard to get one from fluorine. Fluorine has a very high ionization energy because it's extremely hard to get an electron from it. It's almost like neon. Now oxygen is almost as strong as fluorine. It's 2 away. Oxygen has 6 valence electrons. These guys have 5. These guys have 6, 4, 3, 2, 1 valence electron. 7, 8 except helium, of course. So the closer an element gets to being noble or cool, the harder it is to grab that electron. Let's look over here. 3, 2, 1. These guys only have one outside energy level. Outside energy electron. There's only one here. The alkali, group 1, has 1. They're thinking, gee, I gotta get 8 or 7 more. I have to get 7 more electrons to have a total of 8. There's like no way. You know what? You can take my electron. I don't even want it. There's like no way. And the same with these guys. It's easier for them to get rid of 2 than to gain 6. These guys, it's easier for them to lose 3 electrons than to gain 5. So over here, their ionization energy is much less. They're so far away from being noble, from being cool, that why even bother? Especially these guys. Now we'll see later on that once these guys lose these electrons, they do become cooler. They become like the noble gas right before it. So if sodium loses an electron, it'll become like neon. But we will get to that. Just know the trends right now. As we go to the right, it's really hard to get an electron off of them. As we go up, it's also hard to take an electron from them. Trends in ionic sizes are of ions. Cations are always smaller than the atoms from which they were from. And that makes sense because cations are cations because they lose an electron. So they lose electrons in their shell, so they have one less shell. So if we have, let's say, calcium, 2 plus, that's smaller than calcium itself. So we have beryllium, 4 and 9. Beryllium has 4 protons, 5 neutrons. And first energy level, 2 electrons. Second energy level, 2 electrons. Now, beryllium is not happy. It's 6 away from being noble. It's easier for them to lose 2 than to gain 6. Its next previous energy level is filled with 2, so it's stable now. But it did lose 2 electrons, so what's the overall charge? The overall charge here is beryllium 2 plus. Notice this is smaller than the beryllium atom. So this is 2 electrons, and then this is 2 electrons here. Because it lost those 2 outside electrons, it becomes smaller. So the cation is smaller than the atoms from which they came. Let's look at an anion. They're always larger than the atoms from which they came. Anions, remember, get extra electrons. They become more negative because of the extra electrons. So let's look at fluorine. Has 9 protons, 10 neutrons in its nucleus. 2 electrons here. 7 electrons there. It only needs 1 more to be happy. If it gets 1 more electron, it's going to be larger. So that 1 electron is larger. We have that extra negative charge. Remember, it wants to be like neon with a full energy level. It's filled now. We have that extra charge. It's bigger, so it's larger. The fluorine ion, 1 minus, you can also, we're going to get into ions next chapter, but 1 minus or minus is greater than just the normal atom from which it came. Electronegativity. What is electronegativity? So this is a new trend. Electronegativity is the ability of an atom to attract electrons. When an atom is in a compound. So it's really how much do they want a new electron? So this is almost identical to ionization energy, but it's a little different because it's not the amount of energy required to take an electron, it's how much they want a new electron. The values will increase as we go from top to bottom. It looks just like ionization energy, but it's with this caveat here. Who wants the electron more? Well, do these nobles want an electron? No, they don't want electrons. They're already happy. Like, why would these guys want an extra electron? They're happy and stable. So these guys, we exclude them. They do not want an extra electron. They're cool already. We have to get rid of these guys for when we talk about electronegativity, they desire to have a new electron, and we look at Here, this fluorine wants that electron more than anything. It wants to be like neon. So here we have the top electronegative dog. Neon's the stable, the most stable, the coolest person to be like, the coolest atom. Fluorine, it has the highest. These guys don't have electronegativity because if you're cool, why even try to be cool? You don't need anything. Values will increase from left to right across a period. So again, here, these guys are so far from being noble. By adding electrons, they don't want any more electrons. It's easier for this group, the 1s, 2s, and 3s, it's easier for these guys to lose those electrons to be cool, to be like the previous noble gas, than to gain electrons. As it gets closer to a filled outer shell, it really wants an electron more and more. I should say and. So these groups don't want that electron. They'd rather get rid of it, so they don't have electronegativity. These guys, 5, 6, 7, these guys have the most, especially up here. We're going to exclude these fellas.